Hey there, it's Shannon Myers, and today we'll be looking at linear transformations, one of my favorite sections. Let's do it. Images and pre-images of functions. In this section, we will learn about functions that map a vector space V onto a vector space W. This is denoted by T for transformation, and then V maps to W. The standard function terminology is used for such functions. V is called the domain of the linear transformation, and W is called the codomain of T. So what does this mean? If the vector V is in the space V and the vector W is in the space W, such that the linear transformation at the vector V is equal to the vector W, V, that vector, is called the pre-image of W under the linear transformation T. The set of all images of vectors in V is called the range of T, and the set of all V, vectors V in the space V, such that when you input the vector V, you get the vector W out. That set is called the domain of T. Okay, so this is what it looks like. It's a little bit more complicated than we've looked at regular functions before. But what's going on is you have this domain. So this domain here, we're calling this domain vector space V, and this vector space V that's in here, so you have, these little V's in here. V1, vector V2. Actually, they wouldn't be commas. They're just going to be floating around in here. But then, this is the vector V we're talking about. So all those vectors, VI, are the domain of the linear transformation. Okay? Now, the reason there's a codomain is that the range of the linear transformation is like a set within a set. So if you kind of look at this one here, this is where like your W would be, and you might have these different W's, like say W1, W2, let's say they're outside of that range space, okay, but inside of the vector space W. So this thing here is the whole vector space W, and not every single vector in W is the image of V under the linear transformation. Only the W's that are in this area here, okay, or in that space. So this part right here is our linear transformation T, and then we have that V is the domain of T, and W was the codomain of T, and then within W and its own vector space, we would have our T at V, and that's in here, this space here. Okay, so those are all of the possible images you get when you plug in the pre-image vector V. Cool? All right, so that also, by the way, that set is the range of T. So let's take a look at what we have. Example 1. Use the function to find A, the image of V, and B, the pre-image of V. So for A, we've been given that T at V1, V2 is equal to 2 times V2 minus V1, comma, V1, comma, V2. And we've been given vector V is 0, 6, and vector W is 3, 1, 2. First thing to do is figure out what the heck's going on. So this linear transformation, what are we putting in? Beautiful. We're putting it in a vector in R2. So we're going from R2. R2 is the domain under the linear transformation. And then we're going to R3, right? R3. All of R3 would be the codomain, and then all the set of all images in R3 is the range of T. Groovy? Okay, so, all right, what have we been given? We've been given T at 0, 6. Well, what does that equal to? Wherever we see a V1, we'll plug in 0. Wherever we see a V2, we'll plug in 6. So 2 times 6 minus 0, 0, and 6. And where am I getting this? I'm getting this from the V1s and the V2s. We're 6 for V2s, and that's where we got them. Okay, so this is more of a straightforward problem. So then what do we get? We get T at 0, 6. So when I put in the pre-image 0, 6 to T, I'm going to get out the image 12, 0, 6. Cool, cool? So just so you can see what we found, this is what we found. The ordered triple 12, 0, 6 is the image of V equal to 0, 6 under the linear transformation. Cool, cool? Now for part B, let's see what we've got. For part B, we've been given what? This time we're given the W, right? And so we want to find out what the pre-image of that W vector is, if it exists. So you just use what you have, right? We know that T at V1, V2 has to equal to 3, 1, 2. So plugging in what we know about this linear transformation, wouldn't it be true that 2V2 minus V1, V1 and V2 would have to equal to 3, 1, 2, this vector? So how do we figure that out? Beautiful. We use properties of vector equality to solve. So we'll have 2V2 minus V1 must be 3. V1 has to be 1, and V2 must be 2. So since we had V1 and V2 all by themselves, we just need to double check that plugging in 1 for V1 and 2 for V2 will satisfy the top equation. So when we do so, what happens? So we would have 2 times 2 minus 1, is that equal to 3? And yes, 3 equals 3, so that checks out. So what we found out is V equal to the vector 1, 2 is the pre-image of W under the transformation T. Cool, cool? Definition of a linear transformation. Let V and W be vector spaces. The function T, where V maps to W, is called a linear transformation of V into W when the following two properties are true for all U and V and W and in any scalar C. Here we go. The transformation of a sum of vectors must equal to the sum of the transformations of each vector. So this is how you would check. And then the transformation of a scalar times a vector has to equal to the scalar times the transformation of the vector. So a linear transformation is operation preserving. Just kind of like derivatives, when you evaluate the derivative of both sides of an equation. And it is because the same result occurs whether you perform the operations of addition and scalar multiplication before or after applying the linear transformation. So, although the same symbols denote the vector operations in both v and w, you should note that the operations may be different. So for example 2, we want to determine whether the function is a linear transformation. So this transformation, we're going from R3 to R3. So we're putting in an ordered triple and we're getting an ordered triple out. So we want to see if it works. I'm kind of thinking that it's not going to work because of that whole +1 business, all right? So I don't think it's going to be closed under addition, okay? So this is what we do. We take a look and we say, I'm going to let u equal to 1, 2, 3, and really original v could equal to 4, 5, 6. So that means I'm going to provide a counter example because I don't think it's going to work. So if we set up this equation, t at the sum of u plus v, those vectors, we want to know, is this equal to once we apply the linear transformation to u and then adding to that the transformation, applying the linear transformation to v. If I keep u and v together on this left-hand side, what would I be doing? I'd end up getting t at 5, 7, 9. So I just added the vectors u and v. And then continuing on the right side, if I apply the linear transformation to u, what am I going to get? Beautiful, I'll get 1 plus 1, 2 plus 1, 3 plus 1. And then applying the linear transformation to v, I'll get 4 plus 1, 5 plus 1, 6 plus 1. T at u has this output before simplifying, and t at v has this output before simplifying. And I still have not applied the linear transformation to the other one, but what I have done is I've added together the vectors u plus v to get this vector, 5, 7, 9. Groovy? Okay, so applying the transformation to 5, 7, 9, I'll have what? 5 plus 1, 7 plus 1, and 9 plus 1. Is that equal to, this one's going to be 2, 3, 4, plus the vector that terminates in 5, 6, and 7. This represents the applying the linear transformation to the vector terminating in 5, 7, 9. So what do I get for this one? I get 6, 8, and 10. Is that equal to 7, 9, and 11? Nope. T is not a linear transformation. It is a transformation, it's just not linear. In this transformation, what we're doing is we are adding up all the entries in a 2 by 2 matrix. And so what we want to know is this going to be a linear transformation? Well, I'm kind of thinking that this one might work because when I look at what it's going to, I see that it's addition of real numbers, and addition is operation preserving too, right? When you just add a bunch of stuff. So I think it's going to work. And so because of this, I will do the checks in general. So if we let A equal to A11, A12, A21, A22 as our entries. And we'll let B equal to B11, B12, B21, and B23 such that A, IJ, and B, IJ belong to the real numbers for 1 less than or equal to I less than or equal, actually that's a little above the top. We can just say for I equal to 1 and 2. And then we'll also let C belong to the real numbers as well. You want to have your scalar. Here we go. We'll have 2 verifications to make. So for one of them, we want to find out is T at A plus B equal to T at A plus T at B. So that's the first question we're answering. So let's do it. On the left, we'd have T at what? It would be A11, A12, A21, A22 plus B11, B12, B21, and B22. That's our left-hand side. That's T of quantity A plus B. Applying the transformation separately, so when we apply this transformation to matrix A, we'll get A11 plus A12 plus A21 plus A22. And then applying it to the matrix B, we'll get B11 plus B12 plus B21 plus B22. Cool? All right. Now this transformation here will be, we'd be applying the transformation to, we need one happy matrix. So this would be A11 plus B11, A12 plus B12, A21 plus B21, and A22 plus B22. So I just summed those 2 matrices together. And then we want to know, does this equal to? Well, if we take the grouping symbols off and do some commuting, let's see what we're going to get on the right side. We will end up getting A11 plus B11 plus A12 plus B12, so it's looking pretty good. And then plus A21 plus B21, and then finally plus A22 plus B22. So still working on the left, applying the transformation, we'll get A11 plus B11 plus A12 plus B12 plus A21 plus B21, and then plus A22 plus B22, which equals our right-hand side. So that checks out. Cool? All right. So just to kind of recap, the transformation applied to A was this sum right here. The transformation applied to B was this sum right here. And then on the left-hand side, well, we first summed those matrices, right? So applying, once we got to the point where we could apply the linear transformation, we ended up with this stuff here. Groovy? All right. Don't go away. We still have to do the second part. And the second part we have to think is T at our constant times the matrix A. Is that equal to the constant times the transformation of A? Let's do it. So now I want our C times A. So I'll have C times our matrix A within that linear transformation. And I want to find out, is that equal to C times our transformation of A? Okay, so then on the left side, what are we going to get? We're going to get our T at CA11, CA12, CA21, and CA22, completing that scale, bring that scalar in. And is that going to equal to C times quantity A11 plus A12 plus A21 plus A22. So now applying the linear transformation to the left side, I'm going to get CA11 plus CA12 plus CA121 plus CA22. And that is indeed equal to CA11 plus CA12 plus CA21 plus CA22. I distributed the C through those numbers because we're in the real numbers. And so we're good to go. So here's where I applied the linear transformation on the left. And then on the right side, applying the linear transformation just to A. We got all of this here, and then we brought the constant C in. And so that checks out. And so what can we conclude? We can say, yes, T is a linear transformation. All right, so moving right along. Of course, there's some properties of linear transformations. So if we let T be a linear transformation from V into W, where U and V are in the vector space V, then the following properties are true. So if you apply a linear transformation to the zero vector, you're going to get the zero vector out. And if you apply the linear transformation to negative of a vector, well, we just showed it with the constant rule that we could get -1 times the linear transformation applied to V. And then the linear transformation of a difference of vectors is equal to the difference of the linear transformations. And let's do the proof for that one. So we have all of our, our premise. Everything is defined in our premise. So let's start with that left-hand side. T at the quantity U minus V in vectors. Well, if we use properties of vectors, right? What is this going to be? The linear transformation of at U plus negative V, again, still in vectors. And then that's going to equal to what? T at U, because now we have a sum, right? And we've been given that it's a linear combination. So of T at U plus T at negative V. And then that's going to be T at U plus -1 times T at V, which is T at U minus T at V. Cool? If V is equal to a linear combination of vectors, so C1V1 plus C2V2 plus ... plus CNVN, then if you apply the linear transformation, what are you going to get? Well, it would look like T at C1V1 plus C2V2 plus ... plus CNVN. But that in turn is going to be T at, which will be C1 times T at V1 plus C2 times T at V2 plus dot 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 plus Cn times T at Vn. Example 3 now tells us what the linear transformation is, and we need to use properties of linear transformations to find the image that we want. So, T at 1, 0, 0 is 2, 4, negative 1. T at 0, 1, 0 is 1, 3, negative 2. And T at 0, 0, 1 is 0, negative 2, 2. We want to find T at 2, negative 1, 0. So we need to write this as a linear combination of these other vectors, which are what? The I, J, and K vectors. So couldn't we write this as T at 2 times 1, 0, 0 minus 1 times 0, 1, 0, and then plus 0 times 0, 0, 1. But what is that? That is 2 times the transformation applied to 1, 0, 0 minus 1 times the transformation applied to 0, 1, 0, and then plus 0 applied to the transformation of 0, 0, 1, which will just be the 0 vector. So now, okay, what is that transformation at 1, 0, 1, 0, 0? Beautiful. You get 2, 4, negative 1. And that comes from over here. Groovy? All right. And then minus, so T at 0, 1, 0 gives us 1, 3, negative 2. And then I'll just apply this. It'll zero out anyway, but that's okay. Plus 0 times 0, negative 2, 2. And that one came from the third. Cool, cool? Okay, so then what are we going to get? We're going to get 4, 8, negative 2, minus 1, 3, negative 2, plus the 0 vector. And that'll just give us 3, 5, and 0. Cool, cool? Aren't they fun? All right. So now we get to the linear transformation given by a matrix. Okay? So, theorem 2.16. Let A be an m by n matrix. The function t defined by the transformation at the vector v equal to a matrix A times v is a linear transformation, and this is super important, from Rn into Rm. In order to conform to matrix multiplication with an m by n matrix, n by 1 matrices represent the vectors in Rn, and m by 1 matrices represent the vectors in Rm. Okay, so that's something I want you to really look at and think about. Okay? So, here we go. A times V here, so just to give you an example, A has dimension what? Beautiful, m rows by n columns. V has to have dimension n by 1. Just remember, the number of columns in A has to match the number of rows in V. So you end up with your resulting m by 1 vector. Groovy? Okay. So here we go. Define the linear transformation T that goes from Rn to Rm by T at V equals A times V. Find the dimensions of Rn and Rm. So if A is equal to, going across, 1, 2, then negative 2, 4, and negative 2, 2, well, A has dimensions what? Beautiful. A is 3 by 2. Good so far? And what does that mean? Rn is equal to, awesome, R2, and Rm is going to equal to R3. Groovy? All right, so what about this next one? A has dimensions what? Awesome, 3 by 4. So what is our Rn? Equals R4, awesome. And then Rm is equal to R3, very good. So your transformation in this case would be going from R4 to R3. Okay, so next example, consider the linear transformation from example 4, part A. So this first one we were looking at. We want to find out what the image of the vector that's equal to 2, 4 is under the transformation T. Okay? Well, you need to just know this relationship, T at V equals A times V. If we let V equal to 2, 4, that's our input, and W, remember we're going from R2 into R3, and you know this from the dimensions of the matrix, all right? And so W's going to have to just be some W1, W2, W3, and that's what we'll have to find. So our transformation will be, in general, T at V is equal to A times V. So what do we have? T at 2, 4 will equal to A, which was 1, 2, negative 2, 4, negative 2, 2, and then times our V. Now remember, V is going to be what? This is a 3 by 2, so it's going to be a 2 by 1. So you write this as a column vector while you're working the problem. Okay? So then what are we going to get? Good, we'll get a 3 by 1, which is what we want. And so we'll get, what is it? 1, 2 plus 8 is 10. And then negative 4 plus 16 is 12. And then negative 4 plus 8 is 4. And so now the way we want to write this then, when we give our response is T at 2, 4 is equal to the order triple 10, 12, 4. Cool? Okay, and then now let's find the pre-image of negative 1, 2, 2 using the same, we're using the same matrix. So again, having T at V equal to A times V, which of course is equal to W, we would have our A, which it's the same matrix we were using from before, 1, 2, negative 2, 4, and negative 2, 2. And then we don't know this time what V is. So we're just going to write V1 and V2. Last time we had the pre-image and we wanted to find the image. Okay, this time we've got the image and we want to find out if there is a pre-image. Okay, we'll write up here V is equal to V1, V2, and then our W is equal to negative 1, 2, 2. And so we set this equal to our T at V, which was negative 1, 2, and 2. And then how do we solve something like this? What do you think? Beautiful. We just used solve the augmented matrix. So we've got 1, 2, negative 1, negative 2, 4, 2, and then negative 2, 2, and 2. And our reduced row echelon form will be okay, so there's the reduced row echelon form. So what have we found out? Putting that back in terms of a system, we found that V1 equals negative 1, V2 is equal to 0. What does that mean? Our vector V is equal to V1, V2, which is equal to negative 1, 0. I just want you to kind of get used to seeing that. But our result was this linear transformation that we just used a matrix to find. So T at negative 1, 0, if I input that, I get out that desired W, which was -1, 2, 2. Groovy? All right, on to the next. Explain why the vector 1, 1, 1 has no preimage under this transformation. So again, you set up the same situation as we had here, except it would be equal to a different W. So you have your T at V equal to A times V, which in turn is equal to W. We have V equal to V1, V2, and W equal to 1, 1, 1. So, putting it all together again, just so you can see, we would have our A, the same A we've been using, so that was 1, 2, -2, 4, and -2, 2, times V1, V2 equal to, this time it would change to 1, 1, 1. Let's see what we got. Putting this in terms of a matrix, an augmented matrix, we'd have 1, 2, 1, -2, 4, 1, -2, 2, 1. And let's check out what the reduced row echelon form of this is. So the only thing that'll change is the last column will turn into ones. And then we already did that reduced row echelon form command on A, so I'm just going to do second entry to get that command back. And this is what we end up getting, which seems to look okay, doesn't it? But remember, it's augmented. So the first two are fine, but then you get this situation. And what is that telling us? That's telling us that V1 is 0, V2 is 0, and then it's saying that 0 equals 1, which is false, right? So what does that tell us? Beautiful. That tells us that W equal to 1, 1, 1 is an element of the codomain of T, which was R3, right? But not an element of the range of T. Cool, cool? All right, and that's it for today. I hope you have a wonderful morning, afternoon, or evening whenever you're watching this show. And if you like what I'm doing, hey, please subscribe and tell your friends. Bye.